Coming from our new perspective, we need to talk about matrices today, all right? Matrices, plural, matrix, singular, right? We're not talking Keanu Reeves here, although that's an excellent movie if you haven't seen it. It's definitely an old school throwback. Okay, so a matrix, here we go, is a rectangular array, of variables or constants organized in rows, which are our left and right, and columns, which are our up and down. It's usually enclosed in brackets. So a matrix is a rectangular array of variables or constants organized in rows and columns, usually enclosed in brackets. And let's be clear on what we mean by this word array. Let's circle that and swoop a little arrow up here. This is an ordered series or arrangement. An ordered series or arrangement. In other words, the positions that the elements that are inside the matrix are in matter. You can't just jumble them up, okay? The order matters. Just like when we have an XY coordinate, we write the X first and the Y second. We know to graph the horizontal first and the vertical second. So matrices have an organized and ordered pattern to them. Okay, now, the elements of a matrix, those are the individual values within the matrix. And then we use this notation here. I'm just going to use a lowercase a sub xy. Lowercase a sub xy. I could use any variables here, okay? And we use this to denote where x is going to be the row number and y is going to be the column number. We always start at the upper left-hand corner when we're counting rows and columns. If you want to make a note of that, we can say start upper left corner of our matrix. So this is how we can identify specific elements within a matrix, okay? And matrices, by the way, are named using capital letters. You can see here, so like this is matrix A, all right? And within matrix A, we're looking for element A sub 25, A sub 25. So why don't you take a shot at what you think element A sub 25 is? You can write it down here. You can write equals. Write down what you think element A sub 25 is, based on what I just told you up above. You should have put what? -2. -2. Why -2? Because it is row 2, column 5. That's the idea. You read that row 2, column 5. So I go, if I start in the upper corner here, row 2 is going to be, this would be row 1, this would be row 2, and then column 5 is going to be out here like that. So I go row 2, column 5, element A sub 25 is -2. Does that make sense? Everybody see how to read that? Okay. All right, let's try A sub 31. A sub 31. Question? You want to say the answer, Wes? Go for it. Okay, so the answer is 5 for this one. Good. The answer is 5 for this one. Get the idea? Okay, I want you to do 3, 4, 5, and 6, and I'm going to call on you to give me those answers, all right? 3, 4, 5, and 6, and I'm going to call on you to give me those answers. Go ahead and do those now. Is 40. A sub 3, 4, Luca, what did you get? A sub 3, 4. 52 is the right answer for A sub 3, 4. A sub 1, 5. A sub 1, 5, Ike. 21 is the right answer for A sub 1, 5. A sub 2, 2. Daniela, what'd you get? 32 is the right answer. A sub 2, 2. Got it? Identifying the elements within the matrix. Okay? Cool. It's simple, right? Okay, good. All right. Okay, so let's talk about dimensions, all right? So a matrix with m rows and n columns, and again, I'm just using variables here, is said to be an m by n matrix. Okay, make sure we're clear on m by n. That's like a measurement, right? We're talking about dimensions here. It's not m times n. Okay, if we want to find the area of a rectangle, that's what we do, right? M by n. Okay, so then when we're taking a look at these matrices right here, we want to find the dimensions. So tell your neighbor right now, what is the dimension of the matrix in question number 7? What's the dimension? Tell your neighbor. I'm going to ask one of you. You got 5 seconds. 4, 3, 2, 1. All right, Jack, what's the dimension of the matrix in question number 7? Yeah, no, you, Jack. Jack, sorry, triplet. It's a what? It's a 1 by 3. Yeah, that's how we say it. 1 by 3. 1 row by 3 columns. 1 by 3. Okay? Let's do number 8. Tell your neighbor what is the dimensions of the matrix in question number 8. Tell your neighbor what it is. All right, 3, 2, 1. Pygel, what are the dimensions of the matrix in question number 8? It is a 4 by 2. 4 rows by 2 columns. Very good. All right. Tell your neighbor 9 and 10. Tell your neighbor 9 and 10. Coming to you in 5, 4, 3, 2, 1. Sajid, number 9. 3 by 4. 3 rows by 4 columns. Jaden Castro, number 10.
2 by 6.
2 by 6. Very good. 2 rows. 6 columns. So now we can identify the elements by their code, right? We can also determine the dimensions of the matrix. Now, there are just these are just kind of special matrices. We'll just jot them down. Some will come into play, some will not, but we'll notate them so we have a full understanding. So, equal matrices are 2 matrices in which each corresponding element is the same. I'll give you an example. Let's say we had 2 matrices, A and B. The element in the second row first column should be equal to the element in matrix A, should be equal to the element in matrix B, second row first column, and all of the elements would need to be equal. So that would need to be the case for all of the elements in whatever that matrix is. Make sense? Equal matrices. Okay. A row matrix might look something like this. It is a 1 by, could be a lot of columns. A column matrix would look something like this. It's a by 1. This one will come into play. This is a square matrix. And this is when our rows and columns are the same, right? So in this case, this would be a 2 by 2 square matrix, but you could have a 3 by 3 or a 4 by 4 or a number of different square matrices. Okay. Then we could have something called a zero matrix. And this is where all elements equal 0. And it doesn't matter what the rows and columns are. If all the elements in the matrix equal 0, it's called a zero matrix. Now, what we're doing really here, guys, is spreadsheets by hand. That's what we're doing. It's a spreadsheet by hand. Okay, Jack has lost it now. That's really what we're talking about. I mean, if you think about Excel or sheets, it's columns and rows, right? And we're connecting data together. And of course, yeah. Well, but we're not going to do it like we do in writing them in sheets. Okay. However, keep in mind, zeros and ones, that's how all computer programming is done. So really, this is at the heart of all computer science because everything that's programmed is programmed in some combination of zeros and ones. All right, we good so far? Easy enough, right? All right, good. Let's go to the back side. Okay, let's talk about adding and subtracting matrices. Adding and subtracting matrices. Okay? So we can add or subtract matrices if and only if, you're going to want to make sure to highlight that or underline it, box it in. If and only if the matrices you're being asked to add and or subtract have the same dimensions. So the first thing you have to check is, do I have the same dimensions? And then you're either going to add or subtract the corresponding elements with each other. In other words, A11 is going to add or subtract with B11 if you have the same dimensions along those lines. Okay? So, let's take X and Y, matrix X and matrix Y. What are the dimensions for matrix X?
2 by 3.
Okay, so we have let's write this up here. We have a 2 by 3. How about for matrix Y?
2 by 3.
2 by 3. Okay, so we can add those, right? Because they have the same dimensions. So then what is the result of our answer going to be in terms of dimensions? It's going to be a 2 by 3, right? It has to be. Because if we're just adding the elements, we've got a 2 by 3, we're adding a 2 by 3, we're just combining that many elements, we're going to have a 2 by 3 for an answer, right? Okay, so why don't you go ahead and determine what would be the 2 by 3 if we added X and Y together. Go ahead, you come up with that. Come up with this matrix right here. 9, 5, 21, 1, 14, and negative 19. Okay, number 12. Matrix Z subtract matrix W. Let's see if we can do it first. What are the dimensions of matrix Z?
3 by 2.
Okay, so this is a 3 by 2. How about for W? Okay, so we can subtract and add those, right? Okay, good. So let's see what you come up with. Z subtract W. Go for it. Okay, so pay attention to your subtracting of matrices, because if you're subtracting a negative, you're really adding, right?
Yeah.
Okay. The opposite of a negative is a positive. All right, you do 13 and 14. Go.
All right.
If you can't do it, you can just say not possible.
I'm gonna do it. It can be done. That's what I know. But it's 2 by 3 and 3 by 2. But which way do you flip?
Come up with
Yes.
that.
Yay!
Right? Because we can't do W plus X. They do not have the same dimensions. And the order matters, so we can't just flip-flop it or rotate it or twist it around to make it fit. Okay?
Which way would you rotate?
You can't. The order matters, so that's why the dimensions have to be the same. Okay, being clear on the rules for what math you can do based on dimensions is going to become important for us in our functioning with matrices. Okay, one more thing to look at today. Something called scalar multiplication. It's like it sounds. We're going to scale up and or down and possibly into the negatives our elements in each matrice. So, and if we were to do number 15 here, we want 3 times matrix X. So we're going to use the same matrices up above. This time you're going to take each of the elements and you're going to scale them by multiplying each of them by 3. A way, if you look up here real quick, a way you could think about this is you could write out in front of this matrix a 3, and then you're going to take that and multiply each of these elements in the matrix by 3. Okay, go ahead. Scale up X by 3. Let's see what you come up with.
Oh no,
you should have put down this matrix right here. Take a look and see how you did.
I like this small. I like it all.
Yeah? Okay. So 17, you're going to scale X up by -5, or you scale X by -5, and then you're going to add to that Y, which is scaled by 2. Now, for a problem like this, you're going to need to show me at least one level of work in here where you do the scaling, and then you can come up with your answer here, okay? So you need to show me one level of work where you do the scaling, and then come up with your answer as well. Go ahead and do that one.
Oh, we're using these ones from the top. Yes, dude.
So you still need to do 19.
Yeah, I did. I put
All right,
you on.
let me bring you a homework. Stay where you are. That way you don't miss the homework. Homework is all.
Oh, hey, homework is all. Hey, you did
So you have all these and 19. Check 19. All right, you do 19 and finish it on the video, please. Okay, so I did ask you to finish up number 19. Again, you're being asked to distribute here. I think there's an easy way and a harder way to do this problem, but I'm going to put the answer up and we'll talk about it. So if you haven't finished 19, pause now and finish it up. All right, here you go. So I think this is the easier way to do it, is to actually do the W plus Z. Since they have the same dimensions, you can actually add those together first and then do the scalar multiplication, as opposed to doing the distribution. I think you're going to end up writing out more work in larger numbers. Again, you can do it both ways, is fine. And then make sure that you indicate, I like a highlighter. You can see I did that here and here to highlight, to box in your answers. That way it's clear what your final answer is, but you need to make sure to show me some level of work. So like, for example, here, I can tell that you did the W plus Z first because you've got this scalar multiplication out front like that. Okay? All right. We'll see you soon.